Okay, this is the starter for today. Please read this very carefully. Notice that in part B, you need to do it in two parts, delta x1, delta x2. Then you add them together, and then draw a quantitatively accurate kinematic stack. Very important that you draw a picture of this before you begin. So pause the video now and do the problem. Okay, hopefully you've unpaused it. And let's solve this problem. Okay, so what are we given? So given, all right, always draw a little sketch. And so our little car, it said in the problem, it's starting at 0, and we'll just say, hey, we'll say that the position starts at 0 right there. And then for a period of 8 seconds, so delta t equals 8 seconds, we have an acceleration that is equal to 4 meters per second every second. And then we'll reach our maximum velocity. And then we start to slow down. So this is kind of the first part of the problem over here. And then the second part of the problem, well, we come to a stop right here. V final equals 0 over here. And this second part takes 10 seconds. Now we don't know what the acceleration is, but here's what we do know. The final velocity for the first part of the problem is the initial velocity for the second part of the problem. We'll have to use that to solve the problem. So what are we trying to find? Well, I want to know what is that final velocity right here. And then for part B, what is the car's total displacement? What is delta x total? And then part C, we want to draw a kinematic stack. So I'll just abbreviate that KS. So let's solve it. Well, the first part's pretty simple, right? We've got the final velocity. Well, what do we know? We know the initial velocity, the time, the acceleration. We're trying to find the final velocity. Use the first kinematic equation. Plug in your numbers. 0 plus 4 meters per second every second times time, 8 seconds. Seconds cancel seconds. Notice I include units. 4 times 8 is 32, last time I checked, and meters per second. So there's my answer for part A. Now part B, I want to know the total displacement. But what I have to do is break it up into two parts. I need to find delta x for the first acceleration and then add that to delta x for the second acceleration in the second part. So let's do the first part first. Delta x1. Well, if I am going from here to here, I know the initial velocity, I know the time and acceleration. Let's see if we can not have to use that first, that 32 meters per second. I would use the third kinematic equation, which is V naught t plus 1/2 a t squared. And here, the initial velocity was given to be 0. So delta x1 is equal to 1/2 of the acceleration, which was 4 meters per second every second, times the time squared, which was 8 seconds squared. Well, 8 squared is 64. 64 times, well, 4 divided by 2 is 2. 2 times 64 is 100. What is that? 128 meters. Okay? So that's the first part. Now we need to know how far it took. How far did it go to slow down? Okay, and let me zoom out a little bit. Well, to figure out the delta x2, well, what do I know? Well, I always have to know V naught. And V naught is going to be 32 meters per second for the second part. And I know the time, I know my final velocity, and I'm trying to find delta x. I don't know the acceleration, and I don't need to find the acceleration, so I'm going to use the second kinematic equation, which doesn't have acceleration in it. So delta x2 is equal to v naught plus v divided by 2 times time. So delta x2, v naught is 32 meters per second, plus the final velocity is 0 divided by 2, and what's our time? 10 seconds. And I don't need a calculator because 32 divided by 2 is 16. 16 times 10 is 160 meters. So that's how far I went while slowing down. So to figure out my total distance, total displacement from here all the way over to here, I just add these two together. And when I do, I get 288 meters. That's my total displacement. And you have to break the problem up into two parts and then add them together at the end. Okay, now the most complicated part really is, the hardest part I think is to draw that kinematic stack. So let's do that. Okay, we've got position as a function of time. Velocity is a function of time. Acceleration is a function of time. Now, let's go out to 8 seconds. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll just come down like this. And then 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 will be right there. So that's the end. Okay, now notice I knew that my position is going to be positive, my velocity is always positive, but I will have a negative acceleration. So let's figure out, let's do the position versus time graph first. We start at 0, and we're going to go all the way out to 288. So I'm going to do this by 100, 200, 300. Make your life easy, okay? And we know that for the first part of the problem at t equals 8 seconds, my delta x is 128 meters. So I'm going to go, where's 128? Well, here's 150, 128 is right about there. So I know my position's going to be there. And then at 18, I know it's going to be at 288, which would be somewhere like up in there. So that's going to be my position. Now let's do velocity. Velocity starts at 0, ends at 0, but goes up to 32. So I'm going to go 10, 20, 30. This is in meters per second. So 0 up to 32. 32 would be right about there. And then it will slope down to 0 like that. Now the acceleration, well, this has a given acceleration of 4. 1, 2, 3, 4. And this is in meters per second squared. But then for the next, well, it dropped by 32 meters per second in 10 seconds. That's negative 3.2 meters per second. So negative 1, negative 2, negative 3, negative 4, negative 3.2 would be right there. So it's going to look like that. And then this, now let's go back and finish the position versus time. Starts off with 0 slope, then it slopes up to this, and then the slope goes back to 0. So it's going to have two parabolas, a parabola that curves up and a parabola that curves down. Okay? And so this would be negative 4 here. So this, and these are in seconds. Might be a good idea to increment these. This is 8 seconds, and this is 18 seconds right there. Okay, and that is your starter for today. Let's zoom out and take one final look at the solution.